This is AP Calculus 614, Integration Techniques. And in this section, we're really just reviewing all of the different techniques that we've learned in Unit 6 to make sure we're thinking about what type of integration is it. Is it a simple where I can just integrate each term separately? Is it something that I have a natural log situation where I've got a derivative over an original? Is it something where I might have to complete the square or do long division? There are a whole bunch of different situations that we have that we need to understand what we're looking for and how to integrate those. So this section, we're just really going through and redoing some things, putting it all together, and making sure you have those skills that you need to be able to look at any integration problem and understand what to do and how to handle it. So for the first one here, I've got 3x squared plus 4x minus 6 dx, and it's asking us to integrate this. We also need to think about, do I need a plus c at the end, or is this one where I have a definite integral where I can plug numbers in? All of these right here are indefinite integrals, so they will all need a plus c. Remember, that's a common mistake, so if you don't put that plus c, you can get a lot of problems wrong and really lower your grade, so be real careful about that. With this one, that is a simple integration problem where I don't have anything special. I can just integrate each term separately because each one can be its own antiderivative. And I could take the time to separate it and say the antiderivative of 3x squared dx plus the antiderivative of 4x dx plus the antiderivative of negative 6 dx. But there's no need in doing that when we can just do each term separately and add our like terms and be finished. So with this one, remember, when we're integrating, we take the power of the exponent up 1 and then divide by that same power that we end up getting. So this would be 3x cubed over 3 plus this one would be 4x squared over 2, and this one would be minus 6x. Remember, when we have a constant, then the variable of integration will be found in our dx. If this said dy, then we would have a y variable. If this said dt, then the t would be the variable. So it just depends on what this is, the variable of integration, as to which variable we're going to use here. And then I'm going to simplify. That would be x cubed plus 2x squared minus 6x, and don't forget your plus c. For this one, notice that we've got that 2. The 2 could be brought outside if we wanted it to be, but that's a simple integration again as 2t. We used t because it was a dt. For this one, we've got a natural log of x over x, and it's the integral of that. Our variable of integration is dx. For this one, we don't have any formulas that tell us how to take the antiderivative of a natural log. So anytime that happens, where you have something within the problem that doesn't give you don't have any formulas for taking those antiderivatives, that's probably going to be your u part. So this is going to be a u substitution problem where I'm going to let u equal the natural log of x, and so du is 1 over x dx. And if you notice what we've got here, we've got a u on top and a 1 over x dx would be our du. So that's just a simple integration with that u substitution. When I integrate that, I have u squared over 2 plus c. So that would be u squared is natural log of x squared over 2, which is 1/2 times natural log of x squared. And don't forget your plus c. This one is a similar situation. I this time have my natural log on the bottom, but I'm still going to say, okay, my u is still going to be natural log of x because I don't have any way of dealing with that natural log and getting it out of there if I don't do that. So then my du is going to be 1 over x dx. Now, that's the same thing as dx over x, so we've got our du part. Our u this time is on the bottom, so we've got du over u. But if we recognize here that we have a derivative over an original, this is a natural log situation. So that integration is the natural log of the absolute value of u, and then I resubstitute. The natural log of the absolute value of u was natural log of x, and we need our plus c. For the next one, if you look at this, that's 7. It can be brought outside. So I've got dx over 16 plus x squared. There's really I don't have the derivative over the original, because if I did, I'd have a 2x up here over my original. So I don't have any way of doing u substitution and making any sense out of this. So I need to think about my formulas. If I look at this, I've got a 16, which is 4 squared, and I've got an x squared. So couldn't I say that this is one of my inverse trig functions? In fact, if I think back to the inverse trig functions, which one on the bottom didn't have any square root underneath? I believe that would be the arctangent formula. If you consider the arctangent formula, which is right here, du over a squared plus u squared, a would be 4, u would be x. So if I let u be x, if I let a equal 4, and I let du equal dx, we have everything we need here to deal with the arctangent situation. So this is just a 7 times 1 over a would be 1/4. So 7 times 1/4 is 7/4. We've got the arctangent. U over a would be x over 4. And we can't forget our plus c. For the next one, anytime you have an exponential equation, remember we would let the u be our negative 3x, or the exponent part. So my u here is negative 3x, making my du negative 3 dx. Now, I have my e to the u. I do not have my du because I'm missing a negative 3. So this is where I have to offset that u substitution with what's missing. I need the negative 3 here to have the d and the u and the du. I need to offset that on the outside by negative 1/3 so that I've only multiplied by a negative 1, or so that I've only multiplied this by 1 and I haven't changed the value of that integration. So I've got a negative 1/3 e to the u du if I do my substitution. E to the u was negative 3/2, or negative 3x, and then the negative 3 dx is my du. So if I integrate that, remember the integration of an e to the u is just e to the u, so it makes it pretty simple. So we've got negative 1/3 e to the u plus c, and now I resubstitute for my u, and that was negative 3x. And remember, you could always take the derivative of each of these answers to see if you're getting what you started with. In these 3 problems, I've got some different situations. In this one, if I let my u be e to the 2x, and I try to go from there, well, wouldn't my du equal 2e to the 2x dx? If I just try to do some u substitution here, I would have a u over 4 plus u squared, and then I have a dx, which here's my dx, but I don't have the 2e to the 2x to go with it. So this might be a u substitution type of question, but it's not what we're used to seeing. We need to think about how we can tackle this problem to make it something that is workable. I'm going to still let my u be e to the 2x, but I'm going to start thinking about this a little bit differently. If my u is e to the 2x, then my du is still 2e to the 2x dx, but I'm going to think about this as an inverse trig function. If I think about u being e to the 2x, well, wouldn't this right here, since it's e to the 4x, be u squared? So my u squared is e to the 4x, making my u still e to the 2x. And if I have an u squared, and then most of my du is here, but that du is missing the 2, so I'm going to multiply by a 2 here, and then offset it with a 1/2 so that I haven't changed the value of the problem. And then I'm going to let a equal 2. 2 squared is 4. So I've got an inverse trig function here. If I keep the 1/2 and now I substitute, I've got 2 squared plus u squared du, which is an inverse trig function. I keep 1/2 in the front of the inverse trig function. Remember that formula says 1 over a, so 1 over a would be 1 over 2. It's an arctangent. U over a, which is e to the 2x, over a, which is 2, plus a c. And then all I have to do is simplify. 1/4 arctangent e to the 2x over 2 plus c. I tend to resort to the inverse trig functions when I see nothing else will work, especially if I have square numbers added either outside of a square root or inside of a square root, I know it's got to be one of those inverse trig functions. If you're given something like this, if I let u be the bottom, x squared plus 1, then my du would be 2x. Well, there's a bit of a problem here because the top has x minus 3, not just an x. If it just had an x, then it would be a little bit easier to deal with. But what if I recognize that x minus 3, that can be separated into two distinct separate fractions? What if I separate that thing into x over x squared plus 1 minus the integral of 3 times dx x squared plus 1. And I do need my dx here as well. Now, if this is my u part, I do have a natural log situation. The only thing I need here is the du needs a 2 in front, which would leave me with a 1/2 out here. And then for this part, I would have 1/2 the natural log of the absolute value of x squared plus 1. And then for this part, that again looks like an arc-tangent situation where my u is x, my du is dx, and my a is 1. So we have minus 3 times 1 over a, which is 1 over 1, times arc-tangent of u, x, over a, which is x over 1, which is just x, plus c. So right here, that 3 times 1 over 1 is just 3. So we have 1/2 the natural log of the absolute value of the x squared plus 1 minus 3 times arctangent x plus the c. So you see how they could manipulate your equations so that you have some of those inverse trig functions built into the problems. For the third one, I'm going to rewrite this problem. Hopefully you notice that the top there has a higher degree than the bottom. So I can switch this around, x squared plus 1 over 2x dx. I'm going to bring that 1/2 out because if I recognize that the degree of the top is higher than the degree of the bottom, then I'm going to have to do long division to rewrite this problem. And if I do long division, I don't want there to be a 2 dividing into everything. That would complicate things. But I know I can bring constants out. So if I simplify that or rewrite that using long division, I'm going to be dividing the top by the bottom. So I've got x squared plus 0x plus 1. Remember, you have to account for any terms that are missing. And I'm going to divide that by the x that's on the bottom. And I'm just going to do long division. So x goes into x squared x times. I'm going to multiply. X times x is x squared. I will subtract. When I subtract that, I get 0. When I bring down my 0x, that doesn't go in. So now I need to bring down my 1. So we have a remainder of 1. So that's x plus 1 over x as our rewrite. So if I rewrite this, I have 1/2 on the outside, and then that 1/2 is going to be multiplied by the integral of x plus 1 over x dx. Well, that can be then separated again. I've got 1/2 on the outside, the integral of x dx, plus the integral of dx over x. When I integrate that, this would be x squared over 2. This would be the natural log of the absolute value of x. And then that whole thing is multiplied by 1/2. And we do have a plus c. So if we simplify that, we will have x squared over 4, or 1/4 x squared, plus 1/2 times natural log of the absolute value of x, plus c. And remember, you don't need to multiply the 1/2 times the c, because if c is an unknown number anyway, if we multiply 1/2 times an unknown number, we're still going to have an unknown number. So c is just c. You don't have to do anything with the 1/2 there. Here's one. I want you to look at that one, see if you can separate that into several different integrals and get the answer. So pause the video. I'll come back and give you the answer in a few minutes. So here's the answer to that one. The first thing I did was separate this into 4 separate integrals because I think that's easier. Each one has a different skill that you're using. I took the 2 out of this one, and then the antiderivative of cosine x is sine x. So that would be 2 sine x for that term. I kept the minus, and then this is just the integration of x to the 4th dx. Well, that's just x to the 5th over 5, so that's 1/5 x to the 5th, or you could have x to the 5th over 5, that's fine. Plus, this is a natural log situation. You got your derivative over your original, so that's a natural log, the absolute value of the bottom, which was x. And then here I brought the 5 out and recognized that I have an arctangent here. So I have 5 times arctangent x plus c. My u was x, my a was 1 there. Du was dx. So that was a pretty straightforward problem that just involved several different types of integration. Here are some more integration problems. Go ahead and pause the video, see if you can get these, and then I'll come back and give you the answers. So here are those 3 problems. This one, we just had the derivative over the original. So if u is x squared plus 4x plus 2, du is 2x plus 4. And so we end up with the natural log of the absolute value of x squared plus 4x plus 2 plus c. For this one, I noticed that I don't have any x squareds or a squareds. I don't have the derivative over the original. I don't have anything special here. So I manipulate this by completing the square to force it to be an arctangent situation. So when I complete the square, I group the first 2 terms here. I take half of 10, which is 5, and square it. It's 25. I add 25 here, so I subtract 25 here so that I offset it, and I've only added 0 to the denominator. So I have dx over x plus 5 squared plus 1, which is left. So my a is 1, my u is x plus 5, so that makes du dx. So we have an inverse trig function here, arctangent. So we would have 1 over a, which is 1, times arctangent of the u part, x plus 5, plus c, to finish that one off. For this one is a secant squared problem. So the antiderivative of secant squared, remember the derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And if my u part is the x plus 5, if u is x plus 5, then du is just dx. So we just have to write tangent x plus 5 to get d plus c. Taking the derivative of the u part is just 1, so it didn't affect anything. I didn't need to multiply anything in and then offset it with a fraction to make it what we needed. These 10 problems at the end of this video are your assignment. I'm going to come back and give you just the answers in a little bit, but your assignment is to do these 10 problems and then send me a copy of these with their answers and with all the work. Now remember, I'm giving you the answers, so you're going to have to show me the work that you did in order to get credit for this. So take a few minutes, pause the video, copy these down, and then I'll come back and put the answers in a few minutes. Okay, I've written the answers in red, so you can check your answers, make sure you're getting them right. If you have questions, let me know. Show me all the work, and then send me a picture image of this so that I can see what you did to get your answers.